Okay. So this is also not good because it is again, because this is zero, again, the current is increasing, then again decreasing, again increasing, decreasing like this. No? Okay. So it is also not good. Okay. So what you can do is you can send this signal through a full bridge rectifier. Okay. Using a capacitor also, then you will have a smooth AC signal like this. Okay. Maybe this kind of. Okay. So you can send this. Okay. Actually, this DC signal, DC level, you can measure. Okay. So this DC level, this DC level, this DC level is equal to the amplitude. This DC level is equal to the amplitude. Okay. So amplitude, this DC level, by finding this DC level, you can find the amplitude. Okay. Then amplitude, um, using that amplitude, okay, using that amplitude, you can measure the RMS value of this one. Okay. So amplitude divided by √2, this is the RMS value the of this AC current. Okay. Current RMS value. Okay. So that is the way. Okay. So you have to send this AC signal to a full bridge rectifier. Okay. Then you can check the DC signal, output DC signal. Then using DC signal is directly approximately equal to the amplitude. Okay. Then if you know the amplitude, you can measure the RMS value. Okay. So that is the way. Okay. 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 So there are some other instrument also there. Okay. Um, that can be used to measure current and voltage. Okay. So there are this one tout band instrument that is also a modification of a Diasonoval one. Okay. Diasonoval setup. Okay. And there are some electrodynamometer methods. Okay. There are many methods. Okay. But we are mainly focusing on this Diasonoval setup. Okay. Okay. I hope you get the idea about the Diasono setup. Okay. Now, you know how to measure current and voltages using Diasono setup. Current, AC current and DC current using Diasono setup. Okay. So you should have that basic idea. Okay. And then I think we can go, we will see, we will go more to the, that is okay. That's all. Okay. You don't need to read other things. Okay. If you see the Diason setup, that is enough in chapter 2. Okay. So you should understand the exact thing what I have told you. Okay. And so you should see this one also. Okay. You should see this one also. Okay. And okay. So now, um, let's say that, okay, let's say that, let's say that you have a Diasono setup. Okay. You have a Diasono setup. Okay. So that in that Diasono setup, okay, Diasono setup, okay. Let's say that maximum deflection is 90 degree. Okay, maximum deflection is 90 degree. Okay, and the maximum current is let's say that 6 ampere. Okay, so this is the Diasono setup we have seen in our example. Okay. Now you need to you need to upgrade the range from 6 ampere to maybe let's say that 100 ampere. Okay, you need to uh, increase this to 100 ampere. That means you need to change the range. Okay, so if I take some general value, the maximum deflection may be theta. Okay, I think this theta is not maybe not useful. Okay, and the maximum current is, let's say that I max this original maximum current. Okay, let's say that that is ID deflection current. Okay, this is original maximum current, deflection current, maximum deflection current, this one 6 ampere. Okay, and so you need to measure, you need to upgrade this to 100. Okay, so let's say that you need to upgrade this to 100. Okay, that is another current I. Okay, so how we can do this? Okay, so diagonal setup is like this. Okay, here we have a coil. Okay, we have a coil and this coil is like this. Okay, and this is a cable again. Okay, and we have a point here, and we have a scale here. Okay, and this point is fixed here using a spring. Okay, so that is the normal diagonal setup. Okay, so once you send the current through this, there is a magnetic field, and this is the magnetic field is created. Then this pointer will be moved. Okay, so I will write it like this. Okay, so we have a diagonal setup like this. Okay, this is how diagonal setup. Okay, I just draw it somewhat small. Okay, this is the diagonal setup. Okay, now if you want to measure the current, okay, so let's say that you have a circuit like this. You have a circuit like this. So if you want to measure the current using this setup, what you have to do? You have to connect this diagonal setup or this ammeter in series with this circuit. Okay, so you have to cut this here, open this here, then one point should connected to here, one terminal, and one terminal should connected to here. Okay, so serial connected, it is like this. Okay, so if we have this resistor, you have to set your diagonal setup like this. Okay, and again like this. Okay, so this current is flowing through this diagonal setup also. Okay, so this current is flowing through this diagonal setup also. Okay, so this way you have to fix. Okay, this way you have to fix. Okay, actually this coil, normally this coil is made up with maybe using copper. Okay, copper also has a resistance. It has a resistance. Okay, so this coil also has a resistance. Okay, so this diagonal setup will have a resistance. This diagonal setup will have a resistance. That is called as internal resistance. That is called as internal resistance. Internal resistance. Okay, let's say that that is R or something, simple R or something. This is the internal resistance of the diagonal setup. Okay, so this is also just like a resistor. This is also just like a resistor. Okay, so for an ammeter, what is better? The internal resistor is high or internal resistor is low? Which one is better? 1 or 2? If the internal resistor is high or if the internal resistor is low, which one is good? High internal resistance ammeter or low internal resistance ammeters are better? Low internal resistance.
Low in
Yes, low internal. Okay, because if you fix a ammeter here, if this has a significant resistor, here also resistor, so the total resistance will be changed and the current also will be changed. Okay. So you are not measuring the actual current. You are measuring another current. Okay. So if this resistance is very low, this current is will be near to the original current. Okay. So we need low resistance ammeter. Okay. You know that if you have a resistance like this, okay, if you connect a parallel resistance, okay, the total resistance will be dropped. Okay, total resistance will be dropped. Okay, if this is, for example, if this is 0.2, if this is 10, okay, so the total resistance will be less than 0.2. Okay, less than the minimum resistance. If you have parallelly connected the resistance, the total resistance will be lower than the minimum resistance. Okay, so you can calculate it. Okay, 1 over R is equal to 1 over 0.2 plus 1 over 10. Then R will be less than 0.2. Okay. So what I want to tell you is that if you have parallelly connected resistor, then resistance will be low. Okay. So here also I am going to parallelly connect a resistor. Okay. So this is my liaison setup, how I connect it. Okay. So now I remove it. Okay. Now I just connect a resistor parallelly. This is a parallel resistance. Let's say that is R. Okay. So this resistance is simple R. This resistance is capital R. Okay. Okay. So this R is not affected to the performance of a ammeter, because once you connect that this kind of resistor, the total resistance will be reduced. That means that is good for the ammeter. Okay. So this impact, it is a good impact. Okay. There is a good impact if we fix a resistor in parallel. Okay. It is not a bad impact. Okay. So now what happened? Okay. You know that if you consider this one and this one, okay. So the current is coming through this, current is coming through this. Okay. Then the the coming current here, this is a point. Okay. So you can apply Kirchhoff current law. Okay. The incoming current is divided into two. One current is going through this resistor and another current is going through this resistor. Okay. So this may be I1 and this may be I2. Okay. So the voltage between this resistor is I1R and voltage between this resistor is I2R. Okay. I2R. Okay. And I is equal to I1 plus I2. Okay. Okay. So you can get this relation. You can get this relation. Now, what is our target? We need to upgrade this to measure I current. Let's say that this is I max. Okay. I max current. That is 200 mega. Okay. And we have the maximum current that can be measured by the D'Arsonval resistance. Okay. So if this maximum, if you need maximum value, okay, if this is I max is there, okay, some part is going through this one, and the maximum current also will go through this one. Okay. Okay. So the maximum current that can be going through this D'Arsonval setup is ID. Okay. So once when you are sending, when this ID, when this current I is maximum, that is equal to ID. Okay. At that time, the maximum current flowing through this cable also. Okay. So this I max is equal to ID plus this current, that is I2. Okay. Okay. Now this I2 is not important for us. This I2 is not important for us. Okay. We need this Imax ID and this resistance are important also. Okay. So, so simply you can remove this I2. Okay. From this equation, you can get I2 that is equal to R divided by simple R I1. Okay. So now this I1 is actually ID. Okay. Because we are considering maximum current. Okay. So it is equal to ID. So here also it is ID. Okay. So now you can write I max is equal to ID plus R divided by simple R ID. Okay. So what is this? This is a maximum deflection current, maximum current that can be measured by a D'Arsonval setup. This is the max current, maximum current measured by the D'Arsonval setup. Okay. So what is this? Actually, this is the maximum current measured by the total setup. That means including this resistor, including this resistor. If you consider this total, total make a selector. මේ Imax කියන්නේ මෙන්න මෙයාට ඇතුළට යන මේ IR ටයි simple R ටයි දෙන්නටම ඇතුළට යන current එක. හරි. හරි. Total current එක. This is Imax is the maximum current that can be measured by the total setup. Okay. So R is R. Okay. So this equation also important. Okay. So what is the use of this equation? You can simply upgrade your, using this equation, you can upgrade your D'Arsonval setup, to any preferable current, to any preferable maximum current, you can upgrade your D'Arsonval setup to measure any preferable maximum current. Okay. For example, in our, so I have given you an example. Okay. So I ask you to upgrade the D'Arsonval setup to measure 100 ampere. The maximum current that can be measured by D'Arsonval setup itself is 6 ampere. Okay. And internal resistance is should also be given. Okay. Let's say that internal resistance is 2 ohm or something. Okay. Then how we can upgrade to measure 100 ampere? Very easily. Imax is 100 ampere and ID is 6 ampere plus R. Okay, you have to, so if this is a D'Arsonval setup, you have to fix a shunt resistor. This is a parallel resistor, normally referred as shunt resistor. So RSH is given. Okay, so this is normally denoted using RSH. That is a shunt resistance. Okay, parallel resistance RSH. Simple R, that is the internal resistor, that is 2. Then again the maximum current. So here you can calculate the RSH, the shunt resistance. So simply, if you connect a shunt resistor parallelly, you can simply upgrade to 100 ampere. Okay. So that is very easy. Okay. Now there are some, here it is describe these things. Okay. So you can see this. Okay. So once you connect the shunt resistance, okay, so this is the shunt current, okay, so this IM is the maximum, or so the current measured from the D'Arsonval movement or D'Arsonval setup. So now you have example, okay, so 1 milliampere meter movement. Again, this is the maximum current that can be measured by this D'Arsonval setup, okay, and internal resistance is also given. Need to convert to 0 to 100 milliampere. Now it is 0 to 1 milliampere. Now you need to improve it 0 to 100 milliampere. Now this is the maximum current, shunt current. Okay. So calculate the volume of the shunt resistance required. So you can easily calculate using um, using this equation. Okay, using this equation. Okay. Udayan, is that okay? I no need to do this one, no? May example එක හදන්න ඕනේ නැහැ.
Okay.
You can understand it by yourself, okay? Okay.
Okay, sir.
There is another one, okay? There is another one. You can do that one also. The concept is there. Now, okay. Now, if I ask you to, okay, for this example, if I ask you to make this Diason setup to measure 100 milliampere, 200 milliampere, 300 milliampere, like this. What you have to do? Then 100 milliampere, you have, so what you have to do? Here, here it is 99. That is 1 milliampere. 100 minus 1, 99. Okay, so you can calculate the RSH value. Then 200 minus 1, 199. You can calculate another RSH value. Then 300, that is 300 minus 1, 299. You can calculate another shunt resistance. Okay, so if you have this multi-range, what you can simply do is you can simply connect this kind of parallel resistors. Okay, but this resistors you always can't keep connected with the ammeter. Okay, so you have to use a switch here. Okay, maybe like this. Right? So if you want to make this 100 milliampere, you can uh, you can switch this resistance 1.01 resistance. You can simply switch it. Okay, so if you 200, okay, there is another resistance you will get for 200 milliampere. Okay, then at that time you need to switch it here in this one. Okay, so by using this concept, you can make multi-range ammeter. Okay, like this. Okay, this is also I think you can understand. Okay, so here you are asked to design a multi-range ammeter 0 to 10, 0 to 20, 0 to 50 likewise. Okay, I hope you can do this one also. මේකත් පුළුවන් නේද කරන්න?
පුළුවන් වෙයි sir. ඒක මම බලන්න.
එච්චර දෙයක් නැහැ කරන්න හරි?
ඔව්.
So if you have any problem, you can ask me, okay? මේ ගානක් හදන්න.
Right sir.
This one are the same. All are same, okay? So this one also you can do, I hope, okay? So do this up to here, okay? So there are some other setup also, okay? So I think we are not, maybe we no need to focus on this setup, okay? Because that is not in our module outline, okay? So that is enough. You need to understand up to multi-ammeter, multi-range ammeter level using D'Arsonval setup, okay? So just try to do only this example up to 3.3, okay? Up to this one, okay? Okay, so you no need to do this one, okay? Don't do this one, okay? Then this no need, okay? Okay, now I think there are some other ammeter type also. If we have times, we will discuss them later, okay? So this thermocoupler, actually this kind of ammeter we use for high frequency measurement, high frequency current measurement, okay? In maybe in microwave range or RF range, okay? So if you are in RF or microwave field, okay, you have to use this thermocoupler based RF ammeter, okay? So we will see them later, okay? So just now I will, I think that is enough, okay? So we will move to the voltmeter, okay? We will move to the voltmeter, okay? So this is the voltmeter, okay? So first analog voltmeter, okay? So, yeah, here also the Diasono setup is used, okay? Diasono setup is used, okay? So we have a Diasono setup, okay? We have a Diasono setup. Okay, now tell me, let's say that you have a uh, resistor, you have a resistor, okay? You have a resistor, okay? Resistor, you have a circuit, okay? You have a circuit. It can be a resistor or inductor or capacitor, transistor, resistor, anything, okay? So anyway, if you want to measure a voltage between this terminal and this terminal, how you connect your voltmeter? You have to connect your voltmeter parallel. Okay? You have to connect the voltmeter parallel, not seriously. Okay, you have to connect parallel. Okay, so for a voltmeter, do you prefer high resistance or low resistance? For a voltmeter, normally we prefer high
High
resistance. Why? Okay, so if we have a circuit like this, okay, any circuit, okay, transistor, resistor. Let's say that you want to measure the voltage between this resistance, this resistor. Okay. So if this is high resistance, okay, so normally current is flowing through this, okay. If this is high resistance, okay, the current go through this voltmeter is very small, okay, okay, and most of current will go through the component, okay. So the with voltage of the component will be uh, approximately or nearly equal to the actual value, okay. But what happen if you have a low resistance, then most of the current will flow through this and little current flow through this. So once you connect the voltmeter with the low resistance, the voltage drop between this component will be significant. So that is not proper, okay. So we should have low resistance, sorry, high resistance voltmeter. Okay. Now I have a diagonal setup. I have a diagonal setup. Okay. I have a diagonal setup. Okay, like this. Okay. And if you send a current, okay, there is a internal resistance also. If you send a current, there is a deflection. Okay. And there is a voltage between this diagonal setup. Okay. So you know that V equal IR. Okay. Then if you can measure I, okay. So I is always proportional to the V. Okay. I is always proportional to the V. Then also you can calculate V also here. Okay. Okay. Using diagonal setup, you can calculate I also. Okay. Because I and V has a linear relationship. Okay. So because here it has a resistance. Okay. It has a resistance. But this inductance and capacitance values are there. This is not good. This will be not good. Okay. But this inductance and capacitance will be very low. Okay. Okay. So nearly you can measure voltage also using this setup. Okay. So you know that I is related to deflection theta. Okay. And I proportional with V. Okay. So V also proportional to D. Okay. And you can scale this, you can calibrate this, or you can scale this with respect to voltage also. With respect to current, you can do. With respect to voltage also, you can do. Okay. So D'Argenson setup is naturally you can use as a voltmeter as well as a current meter. Okay. Okay. Now this resistance is very low. Okay. So this is not proper. Okay, this is okay for ammeter, but this is not proper for voltmeter. Okay, because if this resistance is very low, most of the current will flow through this one. Okay, to avoid this, what we can do is we can connect a series resistance. Series resistance. Okay, so if you connect a series resistance, the total resistance will be high. Okay, so high resistance voltmeter are preferred. Okay, so we can simply connect a series resistance and you can use it as a voltmeter. Okay, so now you have a resistor here. That is a series resistor, and you have the diagonal setup. Okay, and it's there. Okay, now actually the current is flowing through this. Current is flowing through this. One new. Once you connect this through a terminal, okay, terminal parallelly, the current is flowing through this. Okay, current is flowing through this, and here there is a R also. Okay, so the total voltage between this terminal will be V will be equal to I RS plus R internal. Okay, this is Ohm's law. Okay, okay, this is Ohm's law. Okay, so this I, okay, this I, yeah, is like this. Okay, so now you know that, okay, you know that this I, there is a maximum I that can be measured through this diagonal setup. Okay, there is a maximum I there can be, we can be measured through this diagonal setup. Okay, so that I max is actually we write it as ID deflection current, but here it is they use meter. Here it is mentioned diagonal movement or something. Okay, okay, this IM and ID are equal. Okay, that is identical. Okay, so if you the maximum current, when the maximum current is flowing through this setup, okay, the maximum voltage will be shown here, will be there. Okay, so if the maximum voltage you can measure, okay, is at the maximum deflection point, RS plus R. Okay, so if you know this RS R, okay, and if you can calculate the ID, you can calculate the voltage. Okay, so that is very simple. Okay, so this phenomena is there. Okay, now let's go. Let's try to do this example. Okay, so basic diagonal movement with full scale deflection of 50 microampere. Okay, 50 microampere for full deflection. That means what? Okay, full deflection means what? Okay, if the diagonal setup is there, full deflection means this is a minimum deflection and full deflection is here. Okay, so that pointer is can move up to here. That is the maximum deflection. Okay, okay. So at the full scale deflection, the current is 50 microampere. That means what? This is the maximum current that can be measured by the diagonal setup. This is a maximum current. Okay, so normally it is referred as IM. Okay, but previously we use ID. Okay, don't get confused. Okay, don't mess up. Okay, so this is IM. Okay, that is the maximum current. Okay, so previously I use ID. Okay, don't, this ID and IM are identical. ID and IM are identical. Okay, so don't get confused. Okay, so I will use IM here because in our example also IM there. Okay, so this is the maximum current that can be measured through the Diasono setup. Okay. Okay. And the internal resistance is 500 ohm. Okay. Now you need to measure, you need to upgrade this to measure 10 volt, up to 10 volt. Okay. Okay, up to 10 volt. Okay. So this is the maximum. Okay. Okay. So it is, if it is 500, if it is 500, and the maximum deflection is 50, 500 ohm, and maximum deflection is 50 microampere. This is the maximum voltage that can be measured by the setup itself, Diasono itself. Okay. But this is not equal to 10. Okay. This is very less than 10 because this is a microampere. Okay. So it will be 5525 into 10 to the power minus 3 volt. Okay. So this voltage value is very low. Okay. You need to upgrade it to up to 10. So what the thing you can do? You can simply connect a series resistance with the Diasono setup. Okay. So at the maximum voltage 10, the maximum current should flow through this setup. The maximum current IM is 50 microampere. Okay. Okay. And the shunt resistance, the series resistance you don't know, plus internal resistance R. Okay. That is 500 ohm. Okay. So you can solve this equation to find RS. Okay. So if you connect that amount of that resistance, okay, you can measure this up to 10 volt. You can use this setup to measure up to 10 volt. Okay. So simply calculate the resistance. Okay. Udayanga, did you get it?
Yes, sir.
Yeah.
Good to know.
Those are very simple concept. Okay. So that is why I quickly tell. Okay. So I hope this one also you can do. Okay. Then how you can do multi-range? The same way you have to, if you need to move to the multi-range, what you can do? You can simply connect this kind of multiple resistance with the switch. Okay. So this may be for 10 volt, this may be for 50 volt, this may be for 60 volt. Okay. So if you want to get 60 volt range, you can simply switch, this resistor to the Diasono setup. Okay. So by adding multiple series resistance, okay, with the Diasono setup, you can make this multi-range. Okay. So here also you can the DC voltage also you can measure using a full bridge rectifier. Okay, full bridge rectifier, and then to the Diasono setup. Okay, you can measure the AC volt also. Okay, so basically now you should understand how we can measure AC and DC current and AC and DC voltage using the Diasono setup, and how to improve them to multi-range level. Okay, multi-range ammeter or multi-range voltmeter. Okay, so that example will be enough. Okay, and here also this one also you can do. Okay, you have to calculate the multiple resistance value. Okay, maybe this example also you can do. Okay, you no need to do all this one. Okay. Okay. Also, you can do this one also, no problem. Okay. So try to do these questions. Okay. Try to do these questions. Okay. Okay. So, so that is that, okay. And also just see this sensitivity. Learn this sensitivity terms, okay. We will later learn this, okay, but also just focus on this also, okay. Okay. Uh, okay. Actually, sensitivity is so there are many definition for sensitivity. This is one definition for sensitivity, okay. So check this one also and try to understand by yourself, okay. I will explain this later, okay, because no. Okay. So that is, I think that is enough, okay. So maybe try to do this one also up to example 484. That will be enough, okay. Try to do the example up to 4.8 also, okay. So that will be enough, okay. So that is that, okay. So that is how we can measure AC and DC current and voltage using analog techniques. Okay, these are analog techniques. Okay. Okay. So up to that level, that is enough. Okay. So do this up to this level. Okay. Do this up to this level. That will be enough. Okay. Up to this level. Okay. Up to this level. Okay. No need to try to do these things. Okay. So that will be enough. Okay. Okay. Can you wait for a moment, Udayanga?
Okay, sir, no problem.